it's the first time I talk to an audience with physicists, or in principle primarily consisting of physicists, which is a little risky because I work with models from physics, but I know them very superficially and only from a mathematical point of view. So I hope I won't say anything wrong. If I do, please correct me. I'll try not to say too much about the physical side to avoid making mistakes. But I want to talk about a few models, and this is going to be, I'm going to present a few models in more than just one dimension, or in more than dimension 2, which is the main dimension I want to talk about. But the main focus of all of the work that I'll present is two-dimensional, and one reason for that is that there is a very nice way to create maps between regions in the plane in such a way that, most importantly, angles are conserved. And it's much harder to do that in higher dimensions. So a lot of what has been done in 2 dimensions is much more difficult in higher. It's already difficult enough in 2 dimensions, but it would be considerably more difficult in higher dimensions. So the focus of this talk is on planar models, though many of the models, or all of the models here, can be defined in higher dimensions, and in dimension 1 as well. So I'll talk about 2 models that probably everybody knows, but I don't. Well, maybe for physicists, probably the Ising model is maybe even more a model, familiar model. But I'll start with random walk and random motion, which are in some sense the simplest models for random motion, or the simplest random models. And then I'll talk about a few other models which seem to be very different, which a priori don't seem to have much to do with each other, maybe some similarities, but it turns out that they have that they fall in one same class of processes when you take the scaling limits. So that scaling limit is called the Schramm-Loewner evolution, and I'll talk about that at the end of the talk after I present a few of these models. So so these are models from statistical mechanics, which I probably don't need to define to physicists. But the idea is you have some kind of a model where you have, where the main thing you need to know is sort of local behavior to be able to describe the model. But then you ask questions about, well, what if you have, so imagine you have, these are all models on graphs. So you have a bunch of points and you have some local rules about how to construct this model. Sometimes they're also global, but then you create some configurations and you want to ask general questions about correlations, the shape of interfaces, and so on. And so these are the kinds of questions that statistical mechanics considers. And mathematicians who work in this area are always very much behind physicists, in the sense that the amazing breakthroughs of the last 20 years that have been made by mathematicians were all predicted already by physicists. So physicists have usually what we mathematicians call non-rigorous methods, which means that there aren't full proofs of the results or the conjectures that are being claimed. But for a long time, well, for the last, let's say for the last 40 years, there started to be more conversations between mathematicians and physicists about some of these models. And what mathematicians try to do is look at these models from a more mathematical point of view and try to see if the predictions made by physicists are correct. And usually they are. I can't even think of an example where they're not, but at least none of those I'll talk about. So probability historically has sort of been considered a little bit to be a minor field of mathematics, maybe not quite as serious as other fields, but that has changed. That has changed dramatically with the introduction of this process called the Schramm-Loewner evolution. So we have to thank physicists for giving us a place in the mathematics. So I'll quickly start talking about random walk, and if I'm going too fast, please slow me down, and also if I'm going too slowly, please don't hesitate to tell me that this is too trivial. So random walks can be constructed on all kinds of graphs and lattices. So most of what I'll talk about today are processes that are defined on lattices. The simplest example of a lattice is just ZD. So all the points in d-dimensional space that have integer coordinates. And then all nearest neighbors, all points that are at distance 1 from each other, are connected by an edge. That's one example of a lattice. I'll show you some pictures of a triangular lattice, honeycomb or hexagonal lattice. And those are the main 3 lattices that you'll see today. And so a random walk on such a lattice is, well, in the case of ZD, is a sequence of random variables that are independent, which go towards every possible, which go to any possible, sorry, a sequence of random variables. So it's a sum. So first create a sequence of random variables going in each possible direction in ZD, in the positive or negative direction, and then start adding up steps to create a walk. So if you take the sum, you get what's called a symmetric. In fact, it's even a symmetric simple random walk. There are other symmetric random walks that aren't simple, that are defined slightly differently. But this is the most basic random walk in d dimensions. And so this is supposed to show you the 4 directions in which you can go in K. If you're starting at the central point, and then if you start taking a few steps, you get a picture that looks like this. I don't know where the starting point here is. It could be any one of these points. Then here's a slightly longer 2-dimensional random walk. Here's a 3-dimensional random walk. 2-dimensional random walks intersect themselves a lot. 3-dimensional walks considerably less. And here are some longer 2-dimensional walks. I guess everybody's sort of far away that if you look at the last picture here, this was generated on Z2 on the square lattice, but it's not that easy to tell if you forget about the frame around the picture. It's not that easy to tell what the X and the Y direction are. And so what I'm trying to suggest here is that if you run processes like this for a long time, the orientation of the lattice doesn't really matter anymore. And that's a very important observation, which will lead to the idea of conformal invariance, which we'll talk about a little bit later. Okay, Brownian motion, which I know physicists sometimes consider to be the same thing as random walk, is very closely related. It's a stochastic process, which is just a collection of random variables with some structure. So I'll get to Brownian motion in a second. So the stochastic process can be a very, very general object. It's just a collection of random variables. And the set A could be anything in principle. We also need a normal distribution to be able to talk about Brownian motion. And so this is its density. The importance of the normal distribution comes from the central limit theorem, which says that if you add up a lot of random variables, as long as they're well behaved, that sum is going to start looking normal. And in many cases, fairly quickly. It's definitely the case if they have, well, it's very easy to show if they have 2 moments and are independent, but there are also many relaxations one can make on these assumptions, which still make this hold, or still make the central limit theorem hold. So a 1-dimensional Brownian motion is a stochastic process. So it's a sequence of random variables. In fact, it's a collection of random variables indexed by their usually non-negative reals. And there are a few requirements. Increments on non-overlapping intervals have to be independent. So what happens here and what happens here is independent. The increments have to be normally distributed. And the variance of that normal distribution is the length of the interval. So for shorter intervals, the normal is less likely to jump far. On longer intervals, it might take larger jumps. And then the third requirement, which is a fairly strict one, is that the paths have to be continuous. So the picture you get, so Brownian motion is a distribution on paths. There are uncountably many such paths. So occasionally you'll get a path that's not continuous, but that can happen only with probability, what we call probability 0. So if you get a random sample from that distribution, essentially it has to be continuous. And the non-obvious thing is whether something like this even exists, at least from a mathematical point of view, and it's not a completely straightforward proof. Norbert Wiener was able to show in 1923 that this such an object actually does exist. And yeah, it takes a bit of work. It's maybe a 5 to 10 page proof. Okay, so there are a few properties. So I'll talk about Brownian motion in higher dimensions. And then I'll talk about the connection with random walk. But there are a few properties that are important in what's going to follow. One of these is symmetry of Brownian motion, which from the definition is fairly obvious. So what this means here is that if you take a Brownian motion, which is a distribution really, and reflect everything you have across the horizontal axis, you again get the distribution of Brownian motion. And if you scale time by a factor of c, that's equivalent to scaling space by a factor of root c. So you can basically stretch your Brownian motion by a certain amount in this direction, stretch it by root of that amount in this direction, and you again have a Brownian motion, which of course immediately means that it's a fractal object. Oops. That's related to the notion of non-differentiability. And then if you have a one-dimensional Brownian motion, you can take d of those. And I apologize, I think only probabilists use d for, most people use n for n-dimensional space. We use d, but that's what this means. So take d independent Brownian motions, put one in each dimension, and that's your d-dimensional Brownian motion. The key is that they have to be independent. And there are several nice properties of higher dimensional Brownian motion. It's rotationally invariant. So in the planar case, it's completely clear what that means. In higher dimensions, one has to think a little bit about it. But again, we'll just focus on the plane. So rotate it by any angle around its starting point, and you again have a sample from a Brownian motion. It's scale invariant, which basically means that if you stretch it by the same amount in all directions, you again get a Brownian motion. And so again, it's the same scaling property that we saw in the one-dimensional case. So here's a picture of a one-dimensional Brownian motion, and here a planar Brownian motion. And what these two rectangles here are supposed to show is the scale invariant. So basically, if you just take a piece of your Brownian motion and make it larger, this thing and this thing have the same distribution. They're two samples from the same object, from the same random object. Okay, so these Brownian motions look a little rougher than the random walk pictures I showed you earlier, but if I run these random walks for long enough and sort of make them fit in the frame, eventually we'll get something that's supposed to look a lot like this. But we'll get to that in a second. I want to talk briefly about conformal invariance. So we're going to focus on this object. To talk about conformal invariance, I have to tell you what conformal means. So conformal map between two regions in the plane. Let's think of them as just some simply connected domains. They have to be analytic and bijective. And the reason they're so interesting is that what they do is they, if you have two curves in one domain and then map them to the other domain and look at the corresponding two curves you get out of there, the angles between these curves are the same. And an almost equivalent way of saying this is that if on one side you have a disk, infinitesimal disk, a small disk that gets mapped to a small disk on the other side, the only difference being it might be rotated and it might be rescaled. So basically locally rotations and dilations. So that's a conformal map. And Brownian motion satisfies some of these properties that we find in conformal maps. So it wouldn't be shocking if Brownian motion were conformally invariant. And it turns out it is. So again, the reason a lot of this work happens in 2 dimensions is that if I give you a domain like this, a simply connected domain, another one like this, and it doesn't have to be as nice and regular. This could be a square. It could be a fractal. There is a theorem from complex analysis which says, well, you can find a conformal transformation from whatever this domain is to whatever this domain is. And that's much harder to achieve in higher dimensions. So if you give me 2 domains, I can find a conformal map that sends one to the other. Not necessarily explicitly, but I know I can find one if I really try. Well, I know that in principle I can find one. So what does it mean that Brownian motion is conformally invariant? It means that, so this one started here somewhere, and I ran it until it hit the boundary of this region. And if I send it to another domain through a conformal transformation, well, I can look at the image of this curve on this side. And I can ask, what kind of an object is that? Well, it turns out that is Brownian motion. It is a sample of Brownian motion started from this. So the distribution is exactly the same. So if I want to sample from Brownian motion started at this point and that I run until they hit the boundary of this region, I can do it here and then just send it over there through the conformal transformation. This is particularly useful if you make this region here a disk, because in the disk, we know exactly how Brownian motion behaves. If you give me any point in the unit disk, I can tell you what the distribution on where it exits is, for instance. Okay. And so now there's a connection between Brownian motion and random walk, which is that, as I said, if you run random walk for a really, really, really long time and compress everything and then run for more and compress again, well, you have to compress in this direction and in this direction. And the fact that whatever you compress it by in this direction, you have to take the square root of that to compress it in this direction. And when you've done that for an infinite amount of time, you get Brownian motion. And so here, what this is saying is this hard to read line that started with S of t is just saying our random walk is a discrete object. Imagine you're interpolating linearly between the discrete steps. And then run it for time nt, scale it by root n, and you get a process that's not fractal, because for any given n, it's based on a simple random walk, but in the limit, it becomes fractal. And I won't go into the details of what this means, but this is weak convergence in some sense on a certain space with respect to a certain metric. The interesting thing is, this is true if I have a simple random walk in Z2, but if I run a simple random walk on a triangular lattice in the plane, this still holds. And if I do it on a hexagonal lattice, it still holds. And if I remove simple from the random walk, it still holds. Symmetry is kind of required for this to work as it's written, but there are many, many, many random walks that converge to Brownian motion. And this is what's meant when people talk about universality of Brownian motion. It is a limit of many, many different rescales. It's the scaling limit of many discrete objects. In the same way that the normal distribution is the limit of many sums of random variables. Until I would say the last quarter of the 20th century, this was the only scaling limit of discrete processes that was known to be conformally invariant. Maybe even that was suspected to be conformally invariant. But it turns out this kind of universality exists in several other models. Okay, so I'll quickly talk about phase transitions again, something I probably don't need to tell physicists. But a phase transition is, and the only reason I'm talking about it is that a couple of the models that we'll look at become very interesting at, well, at the place where the phase transition occurs. So the one everyone knows about is ice melts, it becomes water, and water evaporates, becomes a gas, and those are phase transitions. So you change temperature continuously, and there's a point where suddenly there's a radical change in the way the system behaves. So in the second half of the 20th century, there were a few systems that at criticality, which is where the phase transition occurs, were conjectured to be conformally invariant. To understand these systems, so I don't want to talk too much about these systems because I haven't told you what they are, but think Ising model, percolation, and other discrete models like this. To understand how these models work, you have a description, but you don't necessarily know. Right. I won't talk too much about it because I'll describe it in a second, but you don't really know how these systems behave. You don't have any, it's usually not easy for these systems to get much information about the macroscopic behavior. If these systems are actually conformally invariant at the limit, there's a lot you can say about them. And so proving that they're conformally invariant is a really, really important step. So physicists have used methods which I know either nothing or almost nothing about. Renormalization group methods and conformal field theory, which is another area that mathematicians are looking at very closely today. And made amazing predictions for many systems, almost all of which ended up being correct. And then very late in the 20th century, mathematicians started to join the game effectively by proving some of these conjectures or verifying these predictions. Okay, so let me talk about the Lenz-Ising model, which everybody calls the Ising model. But apparently that's not very fair because it seems that so Lenz was Ising's PhD advisor, and he suggested the problem to Ising. And Ising solved the one-dimensional case, which apparently is quite easy, and then made a completely false prediction about what happened in higher dimensions. So some people are a little upset that he got his, that he got his name attached to this very important model. But anyway, so I last night added the lens to all my slides. So imagine you have a graph, and again you can think of Z2, but maybe a box in Z2. Let's think of it as being finite. And on each vertex, you can put a spin. And then you define a probability measure by first computing the energy of the configuration. So this h of omega, omega x is the sign of the spin at point x. So it's plus or minus, +1 or -1. And so you multiply +1s and -1s, and then add them up for all pairs of neighbors in the system on your graph. So this h of omega is really up to an additive constant, the number of pairs of neighbors, the number of neighbors that have opposite signs. So this is called the energy configuration, and then you create a probability measure by looking at exponential of minus beta times this h, and then the z is just a normalizing factor. You divide by all the mass, and you get a probability measure. It's also called the partition function, this c. And understanding the partition function is an exercise people have been engaged in for a long time. Beta has some physical interpretation. It's the inverse temperature. So it turns out that in dimension 2, if you run through betas, So increase your betas, and there's a point at which the system you have moves from being ferromagnetic to paramagnetic. And in practice, you can, I've seen this done. You can take a magnet, and if it's the right magnet and you heat it well enough without burning your fingers, you can actually make it stop working. So if you heat up a magnet, it stops working. The place where that happens is the critical temperature. And that's 1 over beta in our system. Beta equals 0 is not an option in the Ising model, but we'll see what beta equals 0 corresponds to in just a couple of minutes. If beta is 0, what we have is a system where every vertex is equally likely to be plus or minus 1 independently from each other, and that's called the percolation model. So we'll talk about that as well. So here are some pictures. Above criticality, at criticality, and below criticality, and to understand what happened, so this is the kind of picture that had been conjectured to be conformally invariant. And so first question is, what exactly does that mean? How do we phrase this in a way that makes this verifiable? And in particular, what are these? So we have these clusters. What do the boundaries of these clusters look like? Because those are the things that really should be conformally invariant. So can we characterize those? So one way of trying to make this, I'm afraid, I think the video doesn't work, but that matters. Okay. So one way of sort of capturing the structure of these clusters while keeping some sort of mathematical control over where these clusters are is to decide to fix arcs on the boundary of a domain. And so here on the left side, all the vertices are fixed at minus, all the vertices on the right are fixed at plus. And then on the inside, we're running the Ising model. So we're sampling from that probability distribution. So we have a bunch of pluses and a bunch of minuses. How likely they are to be opposites or their neighbors depends on beta. But if we do this, it's not hard to convince yourself that there is necessarily going to be a path from the bottom to the top that has negative spins on its left and positive spins on its right. So in this case, this is here you can see that it works, but it shouldn't be hard to convince yourself that it always works. And maybe this curve has some of the statistical properties that these cluster boundaries have in the picture we saw in the previous slide. Here's another one, a longer one. And in this case, it's at criticality. By the way, the critical temperature is dependent on the lattice. So the critical temperature is not the same on the square lattice or the triangular lattice. But the conjecture is that the interface here at criticality is the same or has the same distribution regardless of what the lattice is, what the underlying lattice is. So the key is being at criticality. So I'll talk about a few more models and then I'll talk, see how much time I have. A few more models and then I'll talk about sort of the unifying idea that brings all these models together. So same kind of setup, we take a graph that consists of edges and vertices. And now this is simpler than the Ising model in the sense that we focus on one vertex at a time, completely independently, and we ask, is it open or closed? Is it, or if you want to color it, is it red or blue? And you pick some probability for, let's say, keeping these sites open, which means that they're there. And then the others are closed with probably 1 minus p. And then we're going to have components of some, we're going to have some kind of a random graph. And components of this graph are what we call open clusters. So I'll show you that on the next slide. Actually, let me show you this first. So here's a percolation configuration. Each one of these vertices of Z2 is kept with a certain probability, P, removed with probability 1 minus P, and then these are the open clusters. So open clusters are connected components of, are maximal connected components of neighbors. Okay, and I went kind of fast through this. For any vertex X, we call Cx the cluster containing that point. And if points are not in any clusters, we consider them empty. We can do the same thing on the triangular lattice. Is this visible or kind of? Yeah, I'll have to change the background. We can do the same thing on the triangular lattice. So the triangular lattice is maybe harder to see than the honeycomb lattice here. It's the dotted lines that go basically between any two neighboring points. And a dual of the triangular lattice is the hexagonal lattice or honeycomb lattice. So you can consider each vertex to be at the center of the face. And then you obtain a new lattice, which where each point has 3 neighbors as opposed to this one where each point has 6 neighbors. It turns out that things are much easier for percolation on the triangular lattice. And so that's why this is the picture I'm showing you. Here's another picture. And so you can see that there are some clusters. I mean, here's one that's disconnected from the rest. I think it's pretty easy to find one that goes from top to bottom or from left to right. But the question is, what's the structure? And again, at criticality, the assumption or the prediction was that there's some kind of conformal invariance here, meaning that basically the same kind of picture is what we saw with the random walk, where if you run it for long enough, you sort of lose the directions of the original lattice that it was constructed on, gets lost, but also that mapping this conformally gives you something that has the same distribution. So let me say a few things about percolation. So absolute Cx is just going to be the number of vertices in the cluster containing X. And now let's imagine we do this on an infinite lattice. We can ask, well, what is the probability that a given vertex X is connected to infinity? In other words, that it's in a cluster that goes on forever. It sounds like maybe it's not too hard a question, but it turns out it is very hard. Of course, the farther out you go, the more chances you have of branching off, but also the more chances you have of being cut off. So it's really not obvious what the answer should be. And of course, it depends on P. And it turns out it doesn't matter which point you pick. That probability here is exactly the same for every vertex in the plane. Or let's talk about Z2 here, or some lattice, some planar lattice. So pick any point, that probably is going to be the same. It's called the percolation probability. And basically, if you start with low P's and start increasing, that probability is 0 for every single vertex. But there's a point where it becomes positive. So if you increase the probability of retaining vertices, there's a point at which the probability that the origin is connected to infinity jumps from 0 to something strictly greater than 0. So this PC is the critical probability for percolation. There's another important quantity, which is the expected size of the cluster that contains the origin. So if we're above criticality, obviously, it means there's an infinite cluster containing the origin, which means that that expected size is infinite. But below criticality, it's not so obvious what happens. So for the percolation probability, as you decrease your P to go towards PC, there's an important exponent that describes what these clusters look like. So, sorry, what the probability of being connected to infinity looks like, how that decays to 0. And for a long time, this beta was unknown for all lattices, and it's still unknown for most lattices. And for the expected cluster size, there's a similar exponent that sort of describes what happens when you go up towards PC. And people had so people could say quite a few things about what happened below PC and above PC, but at criticality, that's where most of the difficult questions have been typically. The value of PC for most lattices is not known. Same thing for beta and gamma. So there are simulations that can give us a sense of what these numbers might be. But in the triangular case, it's known that PC is 1/2. And this was proven already a long time ago. And much more recently, thanks to the tools that I'll talk about in a couple of minutes, the parameters beta and gamma that we just saw on the previous slide were computed exactly. So these are so-called critical exponents, which are key in understanding the behavior of the system at criticality. Okay, so we can do the same thing. So here we're coloring red and white with braid P and 1 minus P. Color all the edges on, sorry, all the vertices on one side of this region in red, on the other side in white, and then run a percolation, sample from percolation on the inside. Again, you're going to have a path from bottom to top that has a white hexagon on the left and a red hexagon on the right at all times. So you can sort of see that this looks like a much rougher path than the one we saw for the Ising model, and that's not a coincidence. So here's the curve. Okay. I'll very quickly talk about a couple of other models, but the self-avoiding walk was introduced by a chemist, who I think got the Nobel Prize, as a model for polymer growth. And so basically it's a model for curves that can't touch themselves and that sort of combine at various angles. So the mathematical model is, let's say again that we're in Z2. The n-step self-avoiding walk is just the uniform distribution on all the paths of length n that don't self-intersect. So it sounds like an easy definition, but counting these, even if I, if I want to keep my kids busy for 3 hours, I can probably tell them, find all the paths that, have length 4, and that could take a while. And if I want to keep myself busy for many hours, I could do it with 10, I think. But the point is, well, I probably try to write code for that instead. But even that is very difficult. So the problem is that well, there's a lot of paths that you would generate. You have to create a uniform distribution. That's the difficulty. You can't just generate a random walk and get rid of all of those that don't intersect. Get rid of all of those that self-intersect. First of all, if you do that, you're going to get rid of most of them. You also can't start a walk and say, well, now I'm going to choose uniformly from all the possible neighbors, because that's not going to be a self-avoiding walk. Either it's not going to be a uniform distribution on paths of length n. So it's very hard. So knowing the number of walks of length n is one of the things people are interested in, or at least getting a sense of how that grows with n. So the conjecture that it grows exponentially with a power correction term. And so, of course, that number mu is the main thing one needs in order to be able to get a sense of how this grows. And again, as a result, so I'm sort of talking about the results of what I will talk about in a few minutes before talking about how this was obtained. But Dimitrov, Pepin, and Smirnov in 2010 were able to show what mu is on the honeycomb lattice. And then there's also the question of what's the mean. So if we want to get a sense of how many walks there are, we also want to know how far they go. So what's the mean square displacement of such a self-avoiding walk? And so there's another conjecture, which is that it grows like n to the 3/2, and that doesn't depend on the lattice. So here's a picture of a self-avoiding walk. So there's one more process that I'll quickly talk about. Self-avoiding walk is sort of of all the models I'll talk about today, it's the one that's resisting mathematicians the most. There's almost nothing that anyone has been able to show except what I just mentioned, this connective constant in the honeycomb case. So one idea would be to try to see if there's a way of mimicking the way self-avoiding walk works by working with a process that's Markov. The problem with self-avoiding walk is that it's not Markovian, which means you can't take a step and then say, okay, now I'm going to decide where I take my next step based on something. All your past steps have a very non-trivial effect on where your next step is going to be. And so there's no easy way to sample from a self-avoiding walk. So maybe doing a simple random walk where each step is completely independent of the previous ones, and then maybe getting rid of all the loops would be a way to produce self-avoiding walks. So that was the hope when Lawler in his PhD thesis introduced the so-called loop-erased random walk. So I'll actually skip this definition, which takes more time to read than necessary. The picture isn't great either, but hopefully it's better. So in this case, the walk goes along the edge where I have a 1, then 2, then 3, then 4, 5, and 6. And every time a loop gets created, the first one that gets created is when the walk gets to this point. So we get rid of this little square. Then it creates another loop. We get rid of the rectangle. And in the end, the loop-erased random walk in this case consists of 3 segments, 3 edges. And of course, you can do this for a long time. And if you do, you get something that looks like this, which if you don't look too carefully, looks a lot like the picture we saw earlier. The hope was at the beginning that they were the same thing. It turns out they're not. But the loop-erased random walk itself ended up being a very important object because it's related to uniform spanning trees, which computer scientists are very interested in. So if you want to generate a uniform spanning tree, there's a beautiful algorithm called Wilson's algorithm, which allows you to generate one, to sample from all the uniform spanning trees on a graph of which there are many, by running loop-erased random walks on that graph and attaching new branches to your tree as time goes. So an important process on its own. And last piece of information before I get to the meat of the talk. We have these curves that sort of these random curves. And we want to kind of find out something about them. How are they distributed? The scaling limit of the Ising interface, the scaling limit of the percolation interface, a loop-erased random walk, a self-avoiding walk. Can we say something about what these distributions look like? And now I'm thinking about these in the scaling limit. So I'm asking what happens to these curves when we run them for a very long time and shrink the lattice. So the key idea here is, and maybe I'll go through this a little quickly because it probably won't help if I go through it slowly because it would probably take more time than I have left to get a good sense of this. But the point is, there is a conformal transformation that can take a disk minus a curve, minus a bit of a curve, and map that to a disk. And when it does that, the tip of the curve gets mapped to a point on the circle. And so if you take a longer curve and sort of imagine stopping at each point on the curve and mapping back and seeing where your image goes, you have a function on the circle, WT, for which you evaluate each time. And okay, so these are all technical things. I'll just mention that this is the ODE in the complex plane that that these maps GT, which send a disk minus a curve to a disk, satisfy. And this has been known for a long time. This W is called the driving function. And then the brilliant idea that Schramm had was there's something that these curves that come from discrete models have in common. And that's, well, first of all, we know that, or we suspect that they might be conformally invariant. And they also have something that's called the domain Markov property, which basically means that if you run them for a while and then stop, and then keep running them, it's the same thing as if you were running them in the restricted domain with the part of the curve removed. So I won't get into too much detail because I could give an entire lecture just on seeing the domain Markov property in one of these examples. It's easiest seen in percolation, which is the thing Schramm was interested in. And so what that led him to realize was that, well, if you take this driving function, so you can start with a curve in a disk, map things, and look at the curve you get on the boundary, or you can start with a function on the boundary and see what sequence of maps that gives you, and what curve would then grow in the disk. And what he realized was if you take the curve on the function on the boundary to be Brown in motion on a circle, you get something which might be the scaling limit of these processes. And the key is the key in realizing that was the domain Markov property. So that Schramm was a brilliant mathematician. He was an avid climber, but unfortunately he died during a climbing trip. And I think everybody regrets all the mathematics that, well, him first of all, and all the mathematics that could have been invented if it'd been around longer. So what I just described was this idea. What I called WT earlier, call that e to the I bkt, which is a way of ensuring that it's a complex number on the circle. And this B is Brown in motion. And this kappa is its variance parameter. So Brown in motion, the way it's usually defined is with variance 1, but you can give it a larger variance or a smaller variance. But it doesn't change qualitatively what Brown in motion is. If you increase the variance of the normals, it looks exactly the same. Maybe let me just say a word about the picture that we saw of this curve inside the disk. That curve will usually tend towards the center of the disk. You can also create Schramm-Loewner evolutions that go from a boundary of the disk to another boundary of the disk. So it all depends on what context you're interested in. If you're trying to grow something from a point in the half plane, let's say from the origin to infinity, that would be what's so-called chordal SLE, because the upper half plane can be mapped to a disk, and then infinity is a boundary point of the half plane. But anyway, those are technicalities that are not very important. The next question was, okay, well, we're trying to put this Brownian motion into the Loewner differential equation. What does that give us? And it gives us curves. If kappa is between 0 and 4, we get a random simple curve, so non-self-intersecting. If kappa is between 4 and 8, we get a curve that has double points that sort of bounces off itself, but it can't cross itself because of the way it's constructed. And these paths on the circular picture I showed hit the boundary of the circle, they hit themselves. And if kappa is bigger than or equal to 8, it's a bit of a headache. It's a space-filling curve that has double points but never crosses itself. So don't try drawing that because you won't be able to. But it's something that exists. And it turns out when kappa is 8, this is the scaling limit of the so-called uniform spanning tree piano curve, which is a space-fitting curve at the limit. Okay. It turns out that the Hausdorff dimension, so the Hausdorff dimension of a curve is basically its fractal dimension. A straight line, the Hausdorff dimension is 1. planar object, it's 2. And then there are objects that are so rough that we can't really say that they have dimension 1. They have to be considered to have a larger dimension, but maybe not quite as much as, if we draw them in the plane, maybe not quite as much as the plane itself. It's a measure of how fractal the object is. And so there's this very nice relationship, which is that it increases linearly in kappa. When kappa is 0, SLE is just a straight line up. That's the only case where it's non-random. So it has dimension 1. All of this is in the plane, so it can have dimension higher than 2. And in between, it just grows linearly. Okay, so here are some pictures. Kappa equals 1, 2, 8/3, which I didn't choose randomly, 3, which I didn't choose randomly either, and 6, which I didn't choose randomly either. It turns out that there's a connection because of conformal invariance between SLE and Brownian motion. So Brownian motion is driving the SLE, but it's, let me see, okay, I'll try to finish in 2 minutes. Brownian motion is driving the SLE, but once it creates a planar SLE, that object also has a connection to planar Brownian motion. And the discovery of SLE and one result related to, basically the discovery of SLE and some of its properties led to Lawler, Schramm, and Werner realizing that if you run Brownian motion for some time, and then look at all the points you can see from you can access from infinity, so it's outer boundary. Mandelbrot had conjectured, I think, in the early 80s, that the Hausdorff dimension of that had to be 4/3. And I think nobody knows how he came up with that conjecture. It's one of the many things that he saw, and we don't know how, but often he was right. But remarkably, SLE was the apparently unrelated, but in fact, very related tool that was required to show this. Partly because some of the critical exponents for SLE are much easier to compute than for other objects. And they're related to critical exponents for Brownian motion, which are needed to be able to compute this kind of thing. So of all the awards that I'll show, this was maybe the least prestigious, but Duplantier, who's a French physicist who's been working a lot with mathematicians on all these questions, had offered a Chateau Margaux in 1982 as a prize for solving this conjecture. And so here's them having that model. And here's Michael Ising, who's also a physicist, a mathematical physicist who's been working on some of these problems. There's Ole Tran, Greg Lawler, and then Werner. And then it was found that these SLEs are actually the scaling limits of many of the objects I mentioned earlier. So SLE 6 is the scaling limit of this rough path that we saw in the percolation picture on the triangular lattice. SLE 3 with parameter 3 is a scaling limit of the interface in the Ising model. And then that was sort of, there's many ways in which you can talk about these scaling limits. In a stronger sense, Smirnov worked with this PhD student and some other co-authors to show this convergence in a stronger sense. And so I don't know how familiar physicists are with the Fields Medal, but it's our Nobel Prize, basically. So it's given every 4 years. And one of the requirements is that you have to be under 40 to get it. So it's given every 4 years to up to four individuals. Oded Schramm was 40 years and 22 days old the year everybody thought he should get it. So those 22 days basically meant he didn't. So Smirnov got the Fields Medal in 2010. Last year, Hugo didn't get it. So Smirnov was for work on percolation in the Ising model. Hugo works on mostly the Ising model and also in higher dimensions. And then SLE2 is the scaling limit of the Looperist random walk. I guess I should put my initials somewhere in this talk. So the B there is me. We worked on finding the rate at which the rate of convergence of the discrete process to the continuous SLE. NSLE8, as I mentioned earlier, is the scaling limit of the uniform spanning tree can occur. And all this work led to Werner getting the Fields Medal in 2006, and Lauder got the Wolf Prize in 2019. So Lauder is not the one who's standing here. So all that is to say that all this work has been really fundamental. It couldn't have happened without physicists making the conjectures that led to mathematicians working on these. Oh, and to finish on a facetious note, I don't know who in the audience is familiar with the Erdős number or the Kevin Bacon number. If you have co-authored a paper with Paul Erdős, you have an Erdős number of 1. If you have co-authored a paper with someone who co-authored with Paul Erdős, you have an Erdős number of 2. And the same thing works with Kevin Bacon in movies. And Beneš Werner has a Bacon number of 3 and an Erdős number of 3. He might be the only person with an Erdős Bacon number, but either way, it's impressive, and it's a pretty low number. Okay, that's all I have.
Thank you very much.